Hello, everybody. So back at the end of the core book in chapter 17, we took a look at trigonometric equations. And by the time we're done with this video, which will finish off the first chapter of our green book, we'll have a much deeper understanding of that topic because we're going to look at a whole bunch of trigonometric identities, which can help us do much more advanced stuff. Quite a lot of this is in the formula book, so I'll make mention of what's there that you do not need to memorize. But there is some material in this video that is not on the formula book that you will want to either memorize or be able to derive on the spot. So section C starts off with three different pairs of formulas, and they're using the Latin pluralization of formula there for whatever reason. It doesn't matter. Anyway, so we have the negative angle formulas. So we're putting in negative theta instead of theta. We've got the supplementary angle formulas because we're subtracting theta from pi or 180 degrees. And then we have the complementary angle formulas there. So for right now, you may choose to memorize all of these, just in case they should come up in a problem. However, if you're like me, you may not have room in your brain to memorize every single formula, so it would be nice if we could come up with these whenever we need them. So for the first one, for the negative angle formulas, once we get through chapter 6, we'll have an understanding of what odd and even functions are. We haven't talked about them yet in this course, but we'll know then that sine is an odd function and cosine is an even function, in which case the negative angle formulas are totally obvious. But if you don't know odd and even functions yet, then we need to have another way to get these. And for all three of these formula pairs, I would say there's three ways that we could think about deriving them. We could either think about function transformations, we could think about the unit circle, or we could even think about right triangle trig. And I'm not going to explain all of those techniques for each of these formula sets, but let's just look at, say, the first one. So first of all, if I think about function transformations, well, and remember, like I kind of don't know that. I just have sine of negative theta here. Well, this tells me that we're going to reflect the graph over the y-axis. But then if I think about what that graph would look like, that's the same thing as reflecting it over the x-axis. So that's how I get negative sine of theta out. If I consider the unit circle, then if I have a negative angle, whatever the sine value of that one is, I know that's in the fourth quadrant, so that's going to have the negative value of whatever the sine was of the one in the first quadrant. And this works whether theta was in the first quadrant originally, or the second, or the third, or the fourth. So that would help me derive the formula. And I guess having a negative angle doesn't really make a lot of sense within a triangle, but here let's look at sine of pi over 2 minus theta. So I've got a right triangle. I know all the angles here have to add up to 180 degrees, which means that these two together have to add up to 90. So let's call that theta. Let's just label some sides here. Hey, that means that this angle, by the way, has to be pi over 2 minus theta, right? So the sine of that angle is going to be A over C, which is the same thing in this picture as the cosine of theta. So that's how you could derive that. So like I said, if you're dealing with some of these, you basically have three different options here: function transformations, unit circle, or thinking about triangles, whichever one you like best. Although there actually is also a secret fourth option that works really well for a few of these, and that is to use other identities that actually are in the formula book. So we'll see that in just a second. Okay, we should be able to use these to simplify various expressions that might show up as these two examples show. So take a look at them, and then we're going to move on to something that is in the formula book, which is the Pythagorean identity, or Pythagorean identities, I would say. And all three of these appear in the formula book on page 7. They're called the Pythagorean identities because, well, you know, it comes from the Pythagorean theorem on the unit circle. So we remember on our unit circle that if we have any random point, the x value of that point is the cosine of the angle. The y value is the sine of the angle. So since it's a unit circle, we know that x squared plus y squared is equal to the radius, which is 1 squared. So that's where we get sine squared plus cosine squared equals 1. All right, and then from there we can derive these last two, but again, they're all in the formula book for us. And really, this one is the one that shows up all the time. The other two are much less common. So here's two examples of rather complicated looking trigonometric expressions that end up simplifying quite a lot, both of which use the Pythagorean identities. The one on the right also uses definitions of the reciprocal trig functions, cosecant, secant, cotangent. But take a little look at these, pause it, read them through, make sure you're comfy, because we are headed to section D. So here we have the double angle identities, and these are all in the formula book, again on page 7. There's only one version for sine of 2 theta. There's only one for tangent of 2 theta. There are 3 for cosine of 2 theta. Depending upon what the problem is that we're working with, one of them will be the easiest one, and the other two will be not as easy. So we just need to think about, like, what do we already know, or what are we trying to figure out? Which one of those is the one that we want to use? So a popular problem type would tell you something about both sine of a particular angle, alpha in this case, and cosine of that angle, and then ask you to work out the sine, cosine, or tangent of 2 times that angle. So, and it's definitely not just going to be 2 times this, right? So sine of 2 alpha, well, we can work out that that should be 2 times sine of alpha times cosine of alpha. We know both of those numbers, so we put it into the formula, and then we know what sine of 2 alpha is. Now, cosine of 2 alpha. This is where we get to make our decision. Which one of these 3 would be the easiest in this case? Well, it probably doesn't really matter because we know in this case sine of alpha and cosine of alpha. So we can put those into any of these. But if I only told you, say, sine of alpha, then you'd want to use the middle formula. If I only told you cosine, you definitely want to use the bottom one. But in this case, it really doesn't matter. They've decided to use the top one. And as for tangent of 2 alpha, well, the easiest thing is going to be just to do sine over cosine, and that's what they do here. Although you could work out what is the tangent of 1 alpha by doing this sine over this cosine, and then you can put that into this formula, and you'll get the same thing. Now, this is another very popular problem type where we're told information about either sine or cosine, and we're then asked to find the exact value of some other functions. And the reason it says exact is because you're not being asked to grab your calculator and do arcsine of 5 over 13 and then get a decimal approximation for the angle and then put that back into your calculator. For these, no, we want to know the exact fractional value. And there's 2 ways that we can approach this. The book's going to show us with a unit circle. So we start off by figuring out, okay, we're told that alpha, our angle, is in the second quadrant, so that means that our cosine value is going to be negative, and that's going to be important in just a second. We then use our Pythagorean identity. Since we know what sine of alpha is, we just put that in, and then we're going to solve for cosine of alpha, but because this is cosine squared, when we take the square root, we're going to get a plus or minus, but we just said it's got to be negative. And then now we know, sine of alpha and cosine of alpha, so we can use the formulas from the previous page to work out sine of 2 alpha and tangent of 2 alpha. But as I said, there is a second method we can use, which is to consider a right triangle. We already know that the sine of alpha is 5 over 13, so we can fill in those sides, and then we can use the Pythagorean theorem, or just recognize the Pythagorean triplet here. This is definitely a 5, 12, 13 triangle. So now we know that the cosine of alpha has to be 12 over 13. And well, using the same reasoning as before, we can work out that it has to be negative. And then you can jump in right over there. So whichever one you like better, Pythagorean identity or Pythagorean theorem on a right triangle, you get to the same spot. We can also work it backwards. So we know in this case that 2 alpha, or cosine of 2 alpha, is equal to 3/4. So then we can determine what cosine of 1 alpha is, and sine of 1 alpha, and tangent of 1 alpha. Now remember that there are multiple formulas for cosine of 2 alpha, so we need to choose the appropriate one. And in this case, the easiest thing to do if we're trying to figure out what just cosine is to use this formula, 2 cosine squared minus 1. We could have immediately used the version using sine squared to answer part B first. We could not have used the formula involving both sine and cosine, of course, because we don't know either of them, at least not in the very beginning. So anyway, answering this problem in order, we can work out what the cosine of alpha is. Again, we need to consider what is the what quadrant is our angle in. We're told that alpha is acute, so that means that the cosine of it is going to be positive. So that can get us that lovely expression for cosine of alpha. And then now we have multiple options to figure out sine of alpha. So they're using, this is actually coming from the Pythagorean identity here. So we could do it that way. We could have also used, again, the cosine of 2 alpha is equal to sine squared minus cosine squared. But we could have also used cosine of 2 alpha is equal to 1 minus 2 sine squared of alpha, so kind of doing it the same way as they did part A. Or we could have used the fact that cosine of 2 alpha is equal to cosine squared alpha minus sine squared alpha, and then we could use this answer that we just got to figure out what sine of alpha is. There's lots of different options we have here, so just choose one that works, and it doesn't really matter which one you like. So now from the double angle formulas, I just want to make mention that there are also half angle formulas, which are not in the formula book, and usually aren't needed, but I feel like occasionally I've seen IB problems where it was nice to know about these. So if we could ignore for just a moment the fact that I typed in 2 equal signs there, just pretend that it's 1. Because of course I've already deleted the document where I typed this all out. We can derive these, the first two you can derive pretty easily. So we know that cosine of 2x is equal to 1 minus 2 sine squared of x. Great, we can then solve for sine of x. That's going to be equal to plus or minus of that whole square root there. That's great. And then if we look in there, if we just change what the angles are, so instead of x, we'll call that x divided by 2. So we're taking half of that angle. So then here, instead of 2x, we'll divide that by 2. Just leave it with cosine of x. And so now we have a half angle formula. So if you know about cosine of x, you can tell me something about sine of x divided by 2. And you can pull the same trick in the second line to figure out the half angle formula for cosine. The tangent one is a little more complicated, but it works. And there's kind of like 2 different answers that you could get out. But that one I don't know that I've ever used. I feel in my heart, I feel as though I've had to use the sine and the cosine half angle formulas once or twice, or at least it made a problem easier than doing it some other way. But maybe I'm wrong. I don't know. Anyway, let's move on. So here are just 2 examples from the book showing how we can use some of these formulas to algebraically manipulate some expressions. Now the book just says, hey, use the identities to simplify these expressions. Well, I don't know. Depending upon your opinion, maybe this answer looks more complicated than that does, because now we have like 2 theta instead of 1 theta, and I think that's a valid opinion to have. So I think in an IB setting, the question would probably say something more like, you know, if you're given this expression, they'd say, rewrite this in terms of 2 theta. And they might not tell you what trig expression to use, but they do tell you that they want 2 theta being in it, and then that leads you to only one possible expression. And so that would be what they're looking for. And this other one, well, they'd say rewrite this in terms of 4b. And so that's kind of giving you a clue in terms of like what you have to do. It's like, hey, I need to get that angle to be doubled somehow. How can I do that? Uh, Start experimenting with your identities and whatnot. Anyway, that brings us to section E, which has our compound angle formulas. And these are, again, in the data booklet, and they are, again, on page 7. You can use them for something simple like this example down below. Expand and simplify sine of 270 plus alpha. Well, you need to know what sine of 270 is for this to work. We should be able to get that out. And now that is using the identities. However, we could have also thought about this in terms of, again, function transformations, because this is the sine graph, but shifted to the left by 270 degrees. And you could imagine, like, what might that look like? Well, it's going to end up looking like a negative cosine. Why is that? Remember that sine starts here in the middle on the way up. And this picture is drawn pretty sloppily, but that's 90 degrees, that's 180 degrees, that's 270 degrees. So that is my sine graph shifted to the left 270 degrees. Now you can use these formulas to derive the original ones that we saw back in section C. If you set A equal to pi, for example, then you can figure out what is sine of pi minus theta, or pi over 2 minus theta. And then since you know what sine and cosine of pi or pi over 2 are, you can then come up with the formulas that we saw back on the second slide of this presentation. So that was the secret fourth method to use. So again, this one, pretty boring. The instructions would probably say to rewrite it in terms of 4 theta. But look, if you see a structure like this where it's cosine of something times cosine of something else, plus or minus the sine of those two somethings being multiplied together, I mean, you got to be able to recognize that that's a compound angle formula, and that's what you need to be using in that problem. Some more interesting examples, and there have definitely been examples of this on previous exams. Something like this, so like sine of 75 degrees, you're not supposed to know what that is off the top of your head, but we can work it out because we know that 75 is equal to 45 plus 30. And once you've figured out that very first step, it's just straightforward application of the compound angle formula. So you can use this to figure out sine, cosine, or tangent of all sorts of other angles, as long as they're combinations of multiples of 30 or 45 degrees. And then add it or subtract it from each other. Now this is a problem type that I like a lot. So you can add or subtract sine and cosine functions together. So those are not like terms because there are different trig functions, but you can still combine them to get a single sine or cosine function out. And remember, that answer could be thought of as a sine function. If we wanted to, it would just be shifted over by a different value of b there. And I guess on an intuitive level, this kind of makes sense if you think about adding the two waves together. If you have any experience with waves from like physics, then adding a wave to another wave should make a new wave. But it's not clear necessarily like algebraically where this comes from. And but we can work this out using the compound angle identities. So let's see how this is going to work out. I like to actually start from the right-hand side, which is dealing with that cosine of x plus b, because that is the compound angle formula right there. So we see that's what they did here as well. And then they just distribute the k into both those terms. Now it's important at this point to recognize that b is a constant, which means that cosine of b and sine of b are also constants. So what we have here now on the right is a term using cosine of x and a term involving sine of x. And guess what we have on the left? A sine of x and a cosine of x. which means that we can set this entire term equal to this entire term, and likewise this one, including that minus, equal to that one. Because we are supposing from the beginning, it says suppose that those two are equal. It doesn't say show that they're equal, it says suppose that they are. Well, they're only going to be equal if the term with the sign on the left is equal to the term with the sign on the right, and if the term with the sign on the left, cosine, excuse me, on the left is equal to the term with the cosine on the right. So we set them equal to each other and we equate their coefficients. So for our cosine, on the left-hand side of the original equation, it's negative root 3, so we see that right here. And on the right-hand side of the original equation, it's k times cosine of b. And then we do the same thing with the sine terms. We set 1 equal to negative k times sine of b. So what that leaves us with is essentially a system of equations in k and b. And the way that I like to think of it then is to take the cosine equation there and solve it for k. So you get k is equal to negative root 3 over cosine of b, and then substitute that value for k into the second equation. And then you can see here that we're going to get tangent of b is equal to 1 over the square root of 3. And that's something that we should be able to solve. And the way the book does it is a little bit different. They divide one entire equation by the other, but you see that they're going to get the exact same thing that we did. And so we solve that and we get that b is either going to be equal to pi over 6 or 7 pi over 6. And both of those b values look valid so far. So what are we going to do? We're just going to try them both and see what happens. So we can begin with pi over 6. So we put that back into, they're putting it into this first equation here, and that's getting them a k value of negative 2. But we're told up here that k was positive. So that means we're going to reject that possibility. And instead, we now know that b has to be equal to 7 pi over 6. So we put that in, and that gives us k is equal to positive 2. And we're done. All right, so try not to forget that. If you ever come up against a sine and a cosine function being added or subtracted together to get you a single sine or cosine function, all you want to do is use your compound angle formulas and then set up a system of equations. It's not that bad. I think the initial problem might look more challenging than it really is. Now that's all of the trig identities that are in our data booklet, but there's some more that are out there. We've already seen some others that are not in the data booklet in this video, but there's some other even like more complicated ones out there. So I want to make a mention of this for a couple of reasons. First of all, I don't like when Math HL students feel like they know all of the math. There's always more math out there, so just here's some trig formulas that are not part of this course currently, but you know, they're out there and people know them, and there's more for you to learn. In fact, these are taken from exercises in our textbook, questions 33 and 34. And I also mention it though because if you are using some resources from different textbooks or perhaps like older versions of this curriculum, because I think these might have been in an older version of the course before I was teaching it, I'm not sure. It can be really helpful to know these. So I've found problems in other textbooks, you know, thinking it was not going to be that bad and then finding out afterwards, oh, I really needed to use one of these things. How the heck was I supposed to know that? Because I certainly don't have these formulas memorized. But I don't know, they're there. If you want to try to stick them in your brain someplace, that'd be cool. And I'll show you some of the previous formulas in action now in a series of progressively more challenging problems. So this one's not too bad. Okay, so what if we're trying to solve this? Sine of x equals sine of 2x. Well, obviously, one possibility is that x is equal to 0. You know, I mean, set x equal to 2x, and then you'll get x has to be equal to 0. And that's true. That'll give us a solution. But there are infinitely many solutions, because, of course, these are both waves that are continuing on forever. So it's going to be more than just that. So we need to do it algebraically. So the way that I would probably think to do it, and that I expect most students in this course would think to do it, is to use the double angle formula right here, and that's great. And then we don't want to divide both sides by sine of x, because then we might lose a solution. We'd actually lose the family of solutions we just came up with, because sine of x might be equal to 0. Instead, we're going to bring everything to one side and then factor. And then we know that either sine of x is equal to 0, in which case we get this infinite family of answers, and of course there's also negatives as well, I didn't mention, or 2 cosine of x minus 1 is equal to 0, which we can then solve for x as pi over 3, 5 pi over 3, and so on. And we can verify this graphically, so I just took a little snapshot from Desmos, and that's wonderful. Not too challenging, but there is another way we could have approached this. If we look at the very first line, and just subtract sine of x from both sides, we get sine of 2x minus sine of x. And then we can use this formula from the previous page. So sine of 2x minus sine of 1x. So we're going to let a equal 2x and b equal 1x. Putting those in here, we get 2x plus 1x, so that's 3x, and then 2x minus 1x, so that's 1x. And then we have to solve this equation. So either cosine of 3x over 2 is equal to 0, in which case 3x over 2 is equal to pi over 2, or 3 pi over 2, or 5 pi over 2, etc. And that would get us these values for x. I forgot the dot, dot, dot there, but you know what I'm going for. Or sine of x over 2 is equal to 0, so then x over 2 is equal to 0, or pi, or 2 pi, which means that x is equal to 0, or 2 pi, or 4 pi, and so on. So this matches the solutions from the previous screen exactly. It's just a different way of getting at them. And maybe you think that this is more complicated because you have to use this crazy formula instead of just the double angle formula and some factoring. Well, that's fine, but things get way worse really fast as soon as we make it be, say, sine of x equals sine of 3x. Because then we need to change sine of 3x into sine of 2x plus 1x, and then we use the compound angle formula on that to get this here. And then we have sines and cosines, so this is problematic, but sine of 2x is going to be 2 times sine times cosines. That gives us a cosine squared here. And then cosine of 2x, I used that as 2 cosine of x minus 1, so we multiply that by the sine of x, and we get these two terms. And then we can combine a bunch of stuff here. So adding sine of x to the left, we get 2 sine of x. Putting these two together, we get 4 sine of x cosine squared of x. Divide everything by 2. Awesome. Now we're over here. We can start to factor things. Oh, no, not yet. I'm sorry. Cosine squared, I changed to 1 minus sine squared using the Pythagorean identity. Distributing through the 2 sine of x. And then bring everything over to one side. And now we can factor, take out the sine from both, leaving us with either sine of x is equal to 0, in which case we get these solutions, or this other factor is equal to 0, which means that sine squared is 1 over 2, which means that sine is going to be plus or minus 1 over square root of 2, or root 2 over 2, and then that gets us these infinitely many solutions. Awesome. We could do all that. None of that is totally outside of our grasp. But we could also do it another way, using that formula from the previous page, and this time just letting a equal 3x and b equal 1x. And then we'll get the exact same answers. And now all of a sudden using this other crazy formula is actually looking much easier than using the supposedly easier formulas. And I'll close out now with like probably my all-time favorite trigonometry problem. And no, it's not my favorite just because I used tau instead of 2 pi. Anyway, if you want to have fun, please pause the video and really like try to work this out. It is fairly complicated, I think, and involves a clever trick to begin to unlock this thing. And by the way, there are exactly 14 solutions on this interval that we need to find. Okay, so let's jump into it. You might be tempted to try to do things with like the double angle formula for the cosine of 2x, and then the double angle formula again for cosine of 4x, because that's 2 times 2x. I don't think that's going to be very promising at all. And if you know things about complex numbers, which we're going to study a little more in depth in chapter 14 of the Green Book, then you might see something in this that makes you think about using a technique from there, but I don't think that's very promising either. Instead, what we're going to do is we're going to be clever here, and we're going to multiply both sides by the sine of x, which is like totally arbitrary right now, but it ends up being kind of nice because that right there is almost a trigonometric identity, right? Specifically, that's equal to, well, if we multiply both sides by 2, then we have 2 times sine of x times cosine of x over here, which is just sine of 2x. And all of a sudden, we start to see this like collapsing pattern, because now I have sine of 2x times cosine of 2x, which means if I multiply both sides by 2, I have essentially sine of 4x. And then I can multiply both sides by 2 again. You can see now why I did the previous 2 examples. Because if we try to evaluate sine of 8x as using the double angle formula and then using a whole bunch of other identities, it's going to be a disaster. It was complicated enough trying to use that method when it was sine of x equals sine of 3x. We do not want to go that route. However, instead, if we just use this other formula, it ends up being not too bad. So we end up getting that either cosine of 9x over 2 is equal to 0, which is going to lead us to these solutions here. That's an infinite family of solution where k is just some integer. Or we solve sine of 7x over 2 equals 0, which is going to get us these infinite solutions, again, where n is just some integer value. And that's going to get us these 2 sets of solutions within the specified domain. And I made a note here that I left these all unsimplified because I think it's nice to be able to see the regular patterns here. Like the first set is just odd multiples of pi divided by 9, and the second set is even multiples of pi divided by 7. Otherwise, if you're looking at in the first case, for example, pi over 9, pi over 3, 5 pi over 9, 7 pi over 9, 1 pi, and so on, it's just not as clear. So I like leaving them unsimplified for now. But then we need to check back into the original equation, because remember I said earlier that there's only going to be 14 solutions, and if you count these up real quick, there are more than that. So if we check these 3, they end up not working. The original equation, by the way, was this one right here, if you've forgotten. So if we put in 0 into that, then we get 1 equal to 1/8. It's not true. If you put in 2 pi into that, you'll also get 1 equal 1/8. If you put in pi, you'll get -1 equals 1/8, I think. So those 3 get eliminated, leaving us with these 14 solutions, which I have simplified here. And yes, you can verify this graphically. Those are the exact solutions. Boy, that was exciting. Now, when we're working with trig identities, part of the difficulty is that there are many trigonometric identities out there, right? There's many even just in the data booklet. So when you're dealing with a trig equation, something you need to solve or simplify or whatever, it's not always obvious which one you need to use. So you need to try something. You just got to go for it. Okay? And the first guess might not be right. That's fine. You've eliminated a bad guess. And the more experience that you get with these problems, the faster you'll be able to kind of determine what is the most efficient way to do a problem. I remember absolutely loving trigonometric identities when I was in high school. I don't know why, because looking back, it's kind of a dry topic. There's not a lot of like application and purpose to it, but I loved just the puzzle of it. So perhaps you will too. And the whole process of going through these problems kind of reminds me of these 2 quotations, which, especially with the Thomas Edison one, it was really hard to source that. Not sure if he ever said that or if those were his exact words, but that certainly is a famous story that he failed at inventing the light bulb. a whole bunch of times, but he didn't look at it that way. He just looked at it as progress. And I want you to take that approach as well with any sort of challenging mathematics or, you know what, any academic subject that you should endeavor in, or non-academic. Progress is progress, whether it comes fast or slow. Keep that growth mindset. Keep improving.